Right, so welcome everyone, good afternoon, or good morning, good evening, wherever you are. So welcome to our weekly call. Hope you've had a fantastic weekend. Let me just share my screen so you can see what we're going to be talking about today. So in terms of our agenda, as you will hopefully be aware, the main focus of our discussion will be on encryption and policy enforcing zero-knowledge middle boxes, which I'll come on to in a moment, which Paul Grubbs from the, excuse my poorly edited slide, Paul Grubbs from the University of Michigan will be talking about. Then we'll cover some recent developments and forthcoming events and some future core topics, but main focus today is on those middle boxes. So Paul, as you can see, if you're looking at your screen, is here. So welcome, Paul, again, as you were here last week, more in listening mode. And as a reminder, at a recent conference, Real World Crypto, Paul gave a presentation. I got some feedback afterwards that was very well received, and it will be a good thing to repeat on this call, which Paul has kindly agreed to do. So without further ado, Paul, if I hand over to you, if you're presenting slides, you should be able to share your screen without a problem.
Yeah, let's try to do that. You see?
Yep, that's working fine.
Okay, so do you see just my slides and not the presenter view?
Yes, just all
right, great. Yeah,
it's quite clear. So
great.
So over to you.
Yeah, thank you very much. Thank you for welcoming me into your call. I'm really excited to be presenting to all of you today. So the talk I'm going to be presenting today is really about resolving a fundamental tension between privacy and policy enforcement in networks, as Andrew sort of alluded to already. So we all know that encryption increasingly is being used to improve the privacy of network traffic. So protocols like TLS 1.3, where a client and a server establish a shared key using some handshake and then use that key to encrypt their data, improve privacy by hiding the contents of network traffic. And increasingly, encryption is being used to hide even the metadata of network traffic. In particular, something that's of interest to everybody here is the use of encryption like TLS 1.3 for DNS queries. So like protocols like DOH and DOT and even oblivious DOH are increasingly used. So encryption makes one of the most basic tasks in network management, which is policy enforcement, much more difficult. Today, networks generally enforce their network policies by using middle boxes to scan traffic directly. So the way this works is a middle box, which if you're not familiar, a middle box is just sort of a network forwarding device that can perform some general purpose computation on the traffic. So the middle box just sort of scans the traffic for policy and checks it for policy compliance. And if it's compliant with the policy, it sort of forwards the traffic out to the internet. And if it's not compliant, it blocks the traffic and potentially bans the user from the network or something like that. So this basic kind of middle box policy enforcement pattern is used to enforce dozens of different kinds of network policies in all different kinds of networks. So things like DNS filtering, like domain filtering, but also things like data loss prevention, like intrusion detection, malware prevention, and on and on and on, firewalls and everything like that. So the basic motivating question of this work is it possible to sort of resolve this tension and have both privacy via encryption and policy enforcement in networks? And so this question is itself pretty contentious. I think in general, many network administrators would argue that we really only should have encryption in networks where policy enforcement isn't required. And cryptographers like myself would generally argue that we should only enforce network policies that don't require sort of access to plain text traffic. So if we want to sort of resolve this tension and satisfy both groups, any solution, we can identify a few basic requirements. The first is that we shouldn't weaken encryption. So we should have just as much privacy for traffic as we had before, except possibly revealing whether the traffic is compliant with the policy or not. So the second requirement is that networks should still be able to enforce the policies that they want to enforce. And in particular, they should be able to identify and block traffic which is not compliant with their policies. And the third requirement is that to make this as easy as possible to deploy, we shouldn't need to change the servers. They're sort of the destination of the traffic. So we believe that in general, this is a good requirement because clients are easier to change than servers in a lot of cases. So for example, in January of this year, only 51% of TLS servers supported TLS 1.3, which is a 4-year-old protocol at this point, whereas 50% of Chrome users were using a version of Chrome that was only 1 month old. So it seems like clients are sort of much easier to change and upgrade than servers. And as a corollary to this ease of deployment thing, we also don't want to introduce additional trust assumptions like new root CAs or trusted hardware on the client or things like that. So there has been some prior work in the academic community on this question, but all of it fails at least one of these requirements. So multi-context TLS and blind box require weakening encryption and also changing the server. And there are a lot of SGX-based solutions out there, but they all sort of crucially require this trusted hardware on the client. So we can additionally identify one very important non-requirement that we really don't want to have in any solution, and that we don't want to prevent circumvention entirely. So what we want to do in any solution is really maintain today's status quo, where sort of circumvention is possible, most people don't do it. So we should still allow circumvention via some kind of, with some advanced users should be able to use some kind of inner encryption like a VPN or Tor or something like this to circumvent the network's policies. Because if we try to prevent circumvention, then we can very easily build tools that can be misused for censorship, which is something that we definitely don't want to do. So in short, we have this challenge where we need to reveal just enough about the traffic to allow the network to verify that it's policy compliant, but we don't want to reveal anything else. And so it turns out that there's a cryptographic primitive that's very well suited to solve this task for us, and that primitive is called a zero knowledge proof. So this primitive is going to come to our rescue, which is sort of the Superman imagery here. So if you're not familiar, a zero knowledge proof is a cryptographic protocol between two parties, which are usually called a prover and a verifier. And a zero knowledge proof allows the prover to convince the verifier of the truth of some public statement with two security properties that are important for our purposes. The first is that it doesn't force the prover to reveal why the statement is true. It just lets the prover convince the verifier that it is true. So this privacy property for the hiding the sort of why is called zero knowledge. And the second security property is that the prover can convince the verifier only if that statement is actually true. So the prover crucially can't convince the verifier of the truth of a false statement. So this property is called soundness. So concretely, we can think of a zero knowledge proof as just being sort of a single message protocol where the prover kind of works to produce a proof, which is just sort of a bit string that it sends to the verifier, and the verifier performs some special verification routine to check whether this proof indicates the truth or the falseness of the statement. So with this zero knowledge proof tool, we can build our solution that resolves this tension, which we call zero knowledge middlebox. So the way a zero knowledge middlebox works is as follows. First, when the client joins the network, it gets a description of the network's policies. Then the client and the server establish shared keys using the same handshake and the same encryption protocols as they did before, and they encrypt their traffic normally. But in addition to sending the traffic, the client also sends to the middle box, which is sort of acting as the network. It sends to the middle box a zero knowledge proof of the statement, my ciphertext that you're seeing me send contains traffic which is compliant with this network policy. And then the middle box, by performing the verification, can verify this proof, and in so doing gain an assurance that the traffic, even though it can't see it, is compliant with the policy that it has set out for its network. So we can just briefly review our 3 requirements and check to make sure that our requirements are satisfied at a high level here. So we don't have to weaken encryption in this zero knowledge middlebox architecture because we use standard encryption as we did before, and the zero knowledge property of the zero knowledge proof hides the underlying traffic of the client's connection. And the middlebox can still enforce the policies because the soundness property of the zero knowledge proof protocol prevents the client from lying and convincing the middlebox that its traffic is compliant when it's actually not. And finally, we don't need server changes here because the server doesn't even really know that this interaction is taking place. So if the middlebox just strips the proofs out of the connection before it forwards the packets to the server, then the server doesn't really even know that there is this protocol happening. So there's no server changes required as well. So when we started this project and sketched this basic architecture out, we weren't sure that it would ever be even close to practical. And the reason why we were skeptical was because prior efforts to deploy zero-knowledge proofs and make them efficient enough for real use cases, like primarily in the blockchain space, have really relied heavily on tailoring the underlying computation that's being proved to the sort of machinery of the zero-knowledge proofs. But we didn't really have this luxury because we have this sort of requirement that we work with standard protocols. We have to sort of take them as they are and adapt our techniques and our machinery to the protocols as they exist. And these protocols in general aren't really made for simplicity, nor are they made for being proved in zero knowledge. So for example, this is, if you're familiar, this is the key schedule of TLS 1.3. And this really pretty hideously complicated diagram is something that we actually had to generate a zero knowledge proof for in this work. So that was definitely a technical challenge. But in the end, we found that not only does this work, but with existing tools, zero-knowledge proofs of properties of TLS 1.3 traffic, including encrypted DNS traffic, are already pretty close to practical, which is a very exciting result for this research. So today in my talk, I'm going to tell you about basically three things about this research. The first is I'm going to go a little bit into detail about the mechanisms that we developed to allow sort of close to practical proofs about TLS 1.3 traffic. And then I'll talk about an application of this zero-knowledge middlebox framework to encrypted DNS. And then I'll briefly touch on some future work and what we're kind of doing right now and what we might continue to do in the future. So actually, if there are any questions, we didn't sort of establish a question protocol here, but if you have any questions, if you have any questions about what I just said or just in general, you can feel free to interrupt me while I'm talking. So I'll pause here for if anyone has any questions.
If anyone can't talk but has a question, just put them in the chat and I will call them out as I see them.
Mm-hmm. Okay, great. Okay. So the first thing, to get a little bit into the mechanisms here, we sort of need to make our zero-knowledge proof protocols a little bit more concrete. So zero-knowledge proof takes as input the statements that the zero-knowledge proof pertains to are circuits, like not exactly digital circuits, but for concreteness, you can think of them that way if you like. So they're basically like wire diagrams consisting of wires and gates. And they take as input two things. They take as input a public input, which is something that the verifier is allowed to see. And they take as input a private witness, which is going back to what I was saying before, sort of the why of why this statement is true, that the zero knowledge guarantee guarantees is hidden from the verifier. So the zero-knowledge proof protocol, the prover runs this prove algorithm that takes as input the circuit, the input, and the witness, and generates a zero-knowledge proof. And the prover sends the input and the proof to the verifier that runs a verify algorithm that takes as input the circuit, the input, and the proof, and then outputs a 0 or a 1. And so if this verify algorithm outputs 1, then the verifier is pretty sure, with very overwhelmingly high probability that this statement is true, but it doesn't it can't sort of extract the witnesses from this proof. So it knows statement is true, but can't learn why, the prover's justification for this. So when we are thinking about zero knowledge middlebox, really our task becomes building circuits that express the kind of policies that the zero knowledge middlebox wants to prove. So once we build a circuit that decrypts the traffic and then checks the compliance of the plain text, we can apply standard tools, standard zero knowledge proof tools to get the prove and the verify algorithms from the previous slide. But because these circuits are really kind of large and complicated because they pertain both to the encryption protocols and the policies, we sort of introduce a pipeline in this paper to sort of help us break this task down into more manageable components. So we have a channel opening circuit that does the decryption. We have a parse and extract that sort of handles extracting the policy relevant data from the plain text network packet in the circuit. And then we have a policy check step that just verifies that this data is compliant. And importantly, the public input of the circuit is going to be the ciphertext that the client is sending, and the private witness is going to be the key that it shares with the server to decrypt that the server will use to decrypt the traffic. So just to narrow in a little bit on one step of this, a challenge, as I mentioned before, is actually building a decryption circuit for TLS 1.3. And so the main question is, how do we actually build a circuit that can decrypt TLS 1.3 traffic? And a first attempt to do this is to just express TLS 1.3 decryption in an arithmetic circuit. And if decryption succeeds, then we just pass the message on to the next step of the circuit. And if it fails, then we just sort of short circuit the rest of the computation and output 0. It turns out that this approach, it doesn't really work and has kind of a severe flaw, which is that the TLS 1.3 decryption protocol lacks a kind of a crucial security property called binding, which means that ciphertext in TLS 1.3 can actually have multiple correct decryptions under different keys. So a malicious client can use this to evade policy enforcement by crafting a ciphertext that decrypts one way and sort of issuing a proof about that decryption, but then having the server decrypt and see a different decryption of the same ciphertext. So we need to sort of prevent this attack if we want to build a secure zero-knowledge middle box for TLS 1.3. So the idea to fix this is that we're just going to be able to add an additional constraint to the circuit. And what this constraint shows is that the key that was passed, that's passed as input by the client to this proof protocol is consistent with the handshake that it performed with the server to establish that key in the first place. So by forcing the client to sort of prove, in addition to the correctness of this decryption, to prove that the key that it inputs is actually consistent with the handshake that it did, that the middle box sees, then we can prevent the client from lying about the key and sort of fix this security problem. But then the question becomes, how do we actually build this key consistency check efficiently? And so I'm going to paper over pretty much all the details here because this is a little bit complicated, but the basic idea is that there's a simple and inefficient way of doing this, which is basically rerunning all of TLS 1.3's key derivation, which is that diagram I showed you before, in the circuit. So we prove in the paper that this works, but it's very inefficient because you have to do a lot of expensive operations in the circuit. So in the paper, we describe this observation that allows us to short circuit most of this expensive operations and basically utilize the fact that the TLS 1.3 handshake has some special strings, but I won't go into too much detail, a little bit more about this. Yep, go ahead. Was there a question?
It doesn't seem like there was, Paul.
Oh, okay.
Carry on.
Okay. So I do want to, so one important thing that I want to highlight about this is that by doing this key consistency check actually can be amortized over an entire TLS session. So in contexts where you're reusing a single TLS session for a long period of time, you can sort of amortize the work of doing this key consistency check. So the way this would work is that at the beginning of your session, when you open it, the client sort of sends a hash of their session key and then a proof to the middle box that the underlying sort of key of this hash is the correct key that was output from this handshake. And then the middle box can store this hash, and then later, rather than rerunning the key consistency check, the client can sort of prove in the circuit that the key that it inputs is consistent with this hash that the middle box already verified is the correct hash of the session key. So in this way, you can sort of cut most of the key consistency work out of the per packet cost of generating these proofs. So this was sort of the more technical part of the talk. So just popping up to the high level again, I told you a little bit about the mechanism of zero knowledge middle boxes and how we got zero knowledge middle boxes to decrypt TLS 1.3 traffic efficiently. But I haven't told you yet about the application of zero knowledge middle boxes. So now I'll move on to describing an application that we tested in the paper, which is building a zero knowledge middle box for filtering encrypted DNS traffic. So I don't need to do any of the DNS background, obviously, for this audience, but basically, DNS is increasingly encrypted because of privacy concerns about DNS queries and the amount of information they reveal to the local network. So increasingly, DNS queries are being sent to it's like centralized resolvers run by Cloudflare or Google instead of local network resolvers, and they're also being encrypted. So this basic pattern is actually becoming the default in a lot of browsers. So for example, like Firefox actually truly defaults to encrypted DNS, and Chrome and Edge also have a default, but in a sort of slightly different way, where they have a kind of auto upgrade. So if your kind of local network allows you to do DNS, or if your local computer's settings allow you to like connect to a resolver that can be auto upgraded, then you can use encrypted DNS. But using encrypted DNS and connecting to a remote or a resolver makes the task of enforcing DNS block lists at the network level extremely difficult or impossible, because the network can't see the traffic kind of by design. They can't enforce this filtering policy and prevent people from resolving domains that are on a block list or something like this. And this tension is particularly acute in networks where filtering is mandated legally. So for example, in the United States, there's this law called the Children's Internet Protection Law that mandates that certain educational and library networks actually filter their networks and sort of filter obscene content to prevent children from seeing things like adult websites. And so because of this law, and because of the protest from network administrators who have to enforce these filtering policies, when Firefox wanted to deploy encrypted DNS by default, they had to build a sort of kill switch into their browser. So when you use Firefox today, by default, when you start the browser, the browser will ask the local network basically if you're allowed to do encrypted DNS. And if the network says no, then it'll just switch back to unencrypted DNS. So essentially at startup time, the browser is forced to ask the network if the network wants to perform a downgrade attack and prevent you from using encrypted DNS, which is a pretty interesting and kind of, I would argue, suboptimal trade-off between privacy and policy enforcement. So this is the kind of trade-off that zero-knowledge middleboxes are really tailored to solving. So in the paper, we describe how we can build a zero-knowledge middlebox to allow networks to enforce DNS blocklisting policies without seeing traffic. So the first step is that the network is going to create a circuit. Yes, Kathleen, your hand is raised.
Yes, and sorry for background noise if you hear any. Let's see. So when you're saying encrypted DNS, are you saying DOS specifically? Because DNS over TLS shouldn't pose a problem for at least those who use a DNS resolver to do that inspection. And that's what we do at Center for Internet Security on behalf of all the state, local, tribal, and territorial organizations. And that's also what CISA has planned in the United States for all federal agencies.
The problem is that the problem with enforcement is I think separate. If I understand your question, it's separate from the protocol that's used to encrypt DNS. The problem is more that the local network is unable to see the traffic. It's not, as I understand it, the problem is not the difference between HTTPS and TLS. Did I understand your question correctly?
No.
Okay.
Let's see. So the way that a large number of organizations in the United States are doing this, so all state, local, tribal, and territorial, and the way that CISA plans to do it, DTLS does still work because you are directing towards a DNS server that does the resolution and does the blocking at that point, as opposed to something that's using ECH or doing some sort of interception. The lock listing is the deny list is at your DNS resolver in those cases.
I see.
So
yeah. So this problem is really more about when networks want to enforce this blocklisting policy with their own like local recursive resolver, and then encrypted DNS sends the DNS traffic to a remote resolver that isn't filtered. So that's the difference, I think.
okay, so there, yeah, okay. I think just your phrasing, I was listening and hearing absolutes, whereas we're getting into very specific things that stop working as opposed to everything.
Right, yeah. So if the network sort of enforces that you go to a filtered remote resolver, then this problem wouldn't necessarily arise. Although with like technologies like oblivious DOH, where the network is unable to see even where your DNS queries are going to, then there would still be a problem with policy enforcement because the network wouldn't be able to verify that you're going to a filtered resolver. Right, and I'm not gonna. I'll come back to that at the end of the talk. And if you want to talk further, we can talk after the I'm done. But yeah, thank you for asking that. Yeah. Yeah, so great question. Thank you for asking for clarification. So the way that this zero knowledge Middlebox is going to work is the first thing the network is going to do is create a circuit, as I described before, that expresses the DNS block listing policy and then creates their block list. So the circuit has this three-step framework that I explained. So it's going to use this channel opening protocol that I described before for TLS 1.3. And then the parse and extract step is going to check the DNS queries, check some constraints about the DNS queries plain text structure, and then extract and deserialize the domain name from that query. And finally, the policy check step is going to verify that the domain name is not a member of this block list set. So this verifying that this domain name is not a member of this set is done using a really standard cryptographic tool called a Merkle non-membership proof. And so when a client joins the network, they get this circuit and a description of the block list on network join. And then they perform a TLS 1.3 handshake with the remote resolver as they did before. And then when they send a DNS query, in addition to the query, they send a zero knowledge proof that this circuit is satisfied on their traffic. So basically, this zero knowledge proof convinces the Middlebox that the underlying DNS query that they're sending contains a domain that's not on the block list. And I'll, sorry, was there a question? Okay, so I won't go super into detail on the mechanism level here, but I will say a couple things. So first, there are a couple of minor differences in the parse and extract step between DNS over TLS and DNS over HTTPS. But overall, these two protocols have very, very similar approaches for doing this zero knowledge filtering. And we can also, in the paper, we describe how we can hide the block list. So in this example, I've depicted the block list as being available to the client, but in some settings, you might not want to reveal the block list. So in the paper, we describe a more complex protocol that uses fancier techniques that can hide the block list from the client, but still sort of maintain this filtering functionality. So I'll just briefly talk about some experimental results. So we benchmarked, in our paper, we benchmarked the key consistency proof that I described and the DOH and DOT case studies with this GROT16 zero knowledge proof system. So we found that the key consistency proof, this baseline that I described as being very inefficient, is indeed quite inefficient. So it adds about 94 seconds of latency to opening a single TLS session, which is obviously very, very much too long to ever be used. But our optimization improves that by a lot. So our optimized protocol only adds about 16 seconds of latency to opening a TLS session, which is about a 6x improvement. And once this TLS session is open, excluding the cost of that key consistency check, we can do a proof of DNS filtering compliance for DOT in about 3 seconds. And for DOH, with the AES cipher suite in TLS, it takes about 6.8 seconds to do a DNS filtering proof. So these numbers are still not practical because adding 3 seconds of latency to every DNS query is a little bit too much to be practical, but we still think this is a very first prototype attempt, and being able to generate a non-trivial zero knowledge proof of anything about network traffic in only 3 seconds, we think is a pretty interesting result. And we have a lot of ideas on how to get this number down even further. So with the little bit of time left, I'll just talk briefly about some future work that we're doing. So what we're doing now is re-implementing our protocols in a new zero knowledge proof system that has better trade-offs for our setting. Yeah, Andreas?
You are saying you're having already some ideas to improve the latency, because I'm fully with you. 3 to 6 seconds is not practical. What is the latency you're envision to achieve in best case?
Yeah, that's a good question. So I might answer your question on this slide. So if you're okay with that, I'll keep going, and then if I'll ask you at the end if I haven't answered it. Okay. Yeah. So with this Spartan proof system, it has much better trade-offs between prover time and verifier time for our settings. So we re-implemented this key consistency check in Spartan, and we found that the improvement in prover time is about 10x. So we can open a TLS session with only about 1.7 seconds of additional latency, which is a huge improvement. And the trade-off here is that the Spartan proofs are a little bit bigger. So the proofs are going to be about 50 kilobytes. But we personally think that this isn't really a showstopper, because in a lot of networks, if you're just communicating to the local network anyway, 50 kilobytes really isn't that much to send. And TLS sessions, especially when they're long-lived, you're not going to be sending this very much. So this isn't really a showstopper. And with Spartan, we haven't finished re-implementing our entire DNS filtering case study, but just for the decryption part of this, which is one of the major costs, like probably like a little bit less than a half of the total cost of prover time, we see another huge improvement. So just the decryption part of this circuit goes down to only about 0.2 of a second in prover time. And we estimate, and this is just an estimate, but we estimate that these costs are going to roughly double in prover time when we re-implement the entire case study. So we estimate if these numbers are borne out by our experiments, then we will be able to do this DOT case study with about maybe 400 or 500 milliseconds of overhead, with a proof that's maybe the proof size isn't going to double, so think like maybe like 32 kilobytes of prover time and maybe 40 milliseconds of verifier time. So we think that this is really exciting, because if these numbers are borne out by our experiments, then 400 or 500 milliseconds of overhead for a DNS query in a lot of settings really isn't that prohibitive, we think. So this is something that is already sort of within striking distance of practicality, and we have some additional ideas on how to get these costs down, especially the proof size. But yeah, so in Andreas, in answer to your question, we're hoping to get down to, in terms of prover overhead, something like 400 or 500 milliseconds. We think is a sweet spot. Again, because DNS is because it's aggressively cached. And I'm saying this, but it could all be very ignorant, so please take it with a grain of salt. But because it's aggressively cached and DNS is in a very latency sensitive application in a lot of cases, 400 or 500 milliseconds of overhead for a DNS query is doable, I think. So that's what we're shooting for.
Thanks.
Mm-hmm. Yeah, so with that, I'll conclude. So just to summarize, in this line of work, we initiated the study of zero-knowledge middleboxes, which resolve tensions between privacy and policy enforcement in networks by allowing the client to issue a zero-knowledge proof of the compliance of their plaintext traffic to the network. So I described an application of zero-knowledge middleboxes to DNS filtering, which allows a client to prove that a DNS query is compliant with a block list. In the paper, we gave two other case studies. One is related to oblivious DOH, and in that case study, we show how a client can prove to the network that their ODOH traffic is destined to a filtered resolver. So basically, even though the network can't see the destination resolver of their traffic, the client can convince the network that their traffic is going to be filtered by the remote resolver. And we also describe a case study that allows the client to prove that the underlying traffic of a TLS connection is HTTP. And we are really excited, and we hope that now you are too. We're really excited about this research because we think that this zero-knowledge middlebox framework has a ton of potential to resolve really challenging tensions in networks between privacy and policy. And it also raises a ton of interesting questions like research questions in cryptography and security and networking and systems. So with that, I'll conclude and take any questions, and thank you for listening.
Great, thanks, Paul. So anyone got any questions, as has been done so far? If you can use the Zoom tool to raise your virtual hand, that'd be fantastic. If you can't or wouldn't be in a position to talk, then as I said earlier, put your question in the chat and I will read it out. But with that in mind, John has raised his hand. So John, over to you.
Hi, thanks for the presentation. Very interesting and lots of questions actually, but I'll try to minimize it to just one or two. The transmission of the policy seems to be a significant hurdle to overcome, meaning that it seems that each client would need to download and then be forced to maintain a very up-to-date policy set, which can number in the millions of items or even worse. Does your paper at all consider how that transmission and state keeping is going to work for n number of clients in a network that has to meet those challenges?
Yeah, that's a great question. In our paper, we mostly don't consider the mechanism of policy distribution, but certainly in a lot of settings, it will be a challenge. I don't have a great answer for you. I think in general, there are some settings where the policy is relatively static. Like a block list policy, where you can imagine that the block list will need to be updated. The sort of fact that you're doing a block list is not really going to change. So the updates there, I think, as long as they're small enough, the updates really won't be a huge hurdle to deployment. But certainly, if the policy is more complex and has more parts, then distributing and sort of more importantly, keeping the clients up to date about what the policy even is could be a big challenge. And I think this is definitely like an area that I'm interested in thinking more about.
Great, thanks. That actually sort of leads to the second part of my question, in that transitive proof of policy compliance. Have you considered how, as an example, and this was brought up, I think it was Kathleen earlier, there is sort of a transitory trust model that's already existing with systems that use a filtered DNS list. But the question of whose filtered list, and can the client prove that it has done a policy examination against an approved list, may actually be an interesting model to pursue. Can you transitorily move the trust proof from as an example, the DNS transaction, then to the middleware box? Is there a way to do that so that you can offload those questions of large policy update sets, as well as the computational work to do that, into a secondary middle box? This is sort of what a DNS filter does today.
Can you, sorry, I don't know that I completely understand your question. Can you say it again?
Sure. Because you got me thinking about how this might work with existing DNS filter sets today. Is it possible that a client could send a DNS query to a trusted DNS filter system, which would then reply back with a proof of policy compliance that could be a third party, meaning it could be operated not by the middleware box operator, but by an external third party, even in an oblivious DNS setting. But the policy had been adhered to, and then a signature essentially of that policy compliance would then be transmitted by the client to the middle box in some fashion, allowing it to gain access to the resource.
Yeah. Okay, I think I understand. So you're saying instead of the client doing everything itself, the client sort of just presents almost like a token of policy compliance, right, that some other party enforced the policy on its behalf. Yeah. That's a good idea. And it actually, I was talking to some people last week, and they also suggested some sort of like token passing model, wherein the client, instead of actually enforcing the policy, sort of proves possession of, like you said, like a signature from some sort of policy enforcing third party. Right. And definitely, like, I haven't thought a ton about this, but I think that's actually a really promising avenue for exploration.
And that really hinges on my first comment, which is these policy sets are very, very large, and keeping them updated, even with well-tuned machines, with high-speed connectivity, is quite challenging. And pushing that out to the client, I think, is going to be a hurdle that is going to be very, very difficult to overcome. So some way to get rid of this, to outsource the policy enforcement to some other system, seems like an interesting one.
Yeah, you could imagine, like you said, the client could connect to the resolver, and then when they want to access an IP, then they present some sort of proof that when they resolve this IP, whoever did it sort of enforced some filtering policy.
Right.
Yeah. Interesting. Okay.
Out of interest, John, I mean, in terms of the overheads that Paul indicated he was targeting, which I think, Paul, you said was maybe of the order of 400 milliseconds for a query. Would Quad 9, John, be? What would Quad 9 think?
Well,
about 100 milliseconds.
That's quite a bit. But again, if you outsource this to a central system that is doing this and can cache those responses, then and I haven't thought about it enough, but I think that if you cache the answers, then you can bring that down to just, it becomes part of the cached DNS query. So So not great, right? 400 milliseconds is pretty large, but you potentially there are ways to mitigate that, and people who are already using a blocking system may already be, or some sort of policy where the middle boxes may already be used to that kind of delay. So I don't know the implications of it.
Thanks. Any other questions from people, or indeed comments? Just building on what you've heard. Give a moment or two to think.
Actually, I have a question, if I may.
Sure, far away, Arno.
Can you hear me?
Yep, loud and clear.
Yeah, sorry. Yeah, so taking a completely different angle to that one, what type of user experience do you see with this? I mean, would you see something like, I don't know, some kind of specific consent, or how would you engage the user in such a model? First, is it desirable? And second, if yes, then how would you do that?
That's a good question. I guess if the user, if this is used, then the user's sort of privacy expectations of their traffic being encrypted would mostly be the same as they would be even if there was no zero knowledge middle box and everything was just encrypted. So I think maybe having some sort of specific user consent maybe wouldn't necessarily be the right model. However, I think educating users about the privacy guarantees of a zero knowledge middle box so that they sort of become comfortable with the idea that you're issuing a proof and it discloses the minimum amount necessary to allow the networks to enforce their policies. I think doing that and sort of building consent among the users more generally, I think is an important task for deploying this. Because the users to get comfortable with the idea, I think will need to sort of be educated about what it means for their privacy to have this zero knowledge proof. But it's not something I've thought a huge amount about, but it is definitely an important challenge.
Okay, thank you. Because I was thinking the case of an enterprise employee in a which would be, so I was not thinking too much about, I understand your examples on DNS with filtering for children and so on. I was thinking more about more complex enterprises cases, where here I think John is right. There would be a lot of policy to prove, but I find it an interesting idea actually to have a. I didn't realize you could have this type of approach. So I'm very new to that, so I can't really judge yet. But I find it an interesting approach. But in an enterprise case, I mean, imagine when you have today when you have proxies that try to enforce very complex policies for for shadow IT type of cases, for zero trust type of cases, for all of that. What would be your take on that, actually, if you have any idea for enterprise environments? Because here we have done DNS example, but let's imagine we have more complex network security cases.
Yeah, I can't say that I know enough about really like concrete enterprise network policies to be able to like speak intelligently about what it would look like. I guess on the purely like mechanism level, zero knowledge proofs are expressive enough to capture any computation you want. So at least theoretically, you could prove any policy you want about the traffic. As for whether it's efficient enough to do that and whether the policy updates would become prohibitive in practice, I just don't know.
Okay. Thank you.
Thanks, Arno. And any questions from anyone else or comments on the sort of the overhead, and is this something you might be interested in if you're already running a encrypted DNS resolver? Not seeing any raised hands at the moment. I don't see any questions in the chat. Okay, let's pause there then. I think Paul, I think you've given people a lot of food for thought.
And if people have questions that they think of after the meeting, please feel free to just email me. I think probably Andrew. Well, Andrew has my email, but I can also just put it in the chat.
Sure. And I'll share. People already should have it, but I will share afterwards again the link to the paper, which sort of gives more detail than Paul could reasonably go through in the slides. Just so you've got that to sort of back up the discussion. But well, thank you, Paul. I think that was very helpful, and I think we'll give people plenty of food for thought as an alternate way of sort of solving the sort of privacy versus policy conundrum in a way that potentially pleases all interested parties without either having to compromise, which is always a good thing in mind. So yeah, I think that is a very interesting project. So thank you for taking the time to share that with us.
Yeah, happy to do it.
Okay, let's then change tack from that. So I'll go back to my slides, if you just bear with me a moment whilst I go back to the correct screen. And just give you a quick heads up on a couple of recent developments. So these are from the weekly email, which you would have received earlier. I'm not going to go through all of them, but quite timely in a way, I suppose. I will highlight there's a sort of recently, I think last week in the States, a court order from a sort of copyright rights holder requiring ISPs to block access to some specific sites in the phrasing as used by the order by any technological means available to the ISP's systems, which is quite a broad sort of set of requirements. That was the outcome of the case. So that whether that's going to go to appeal, I've absolutely no idea. But I thought that was interesting to see that. So maybe something like a sort of zero knowledge middle box would be a more acceptable way of doing that to those people that have privacy concerns. And then a sort of similar, well, in some ways similar sort of requirement in the UK, but driven by sort of from a different direction, which is a requirement for ISPs, app store providers, and social media companies to block access to both to specific Russia-related sites and also to bar provision of service to named people and organizations. This is all linked to Russia-related sanctions, which sort of came out in the UK last week, and I think there's still more detail coming out about that this week as well. The links are provided. You can read those and a few other things at your leisure. Also wanted to highlight, I got some forthcoming events, many of which are face-to-face or hybrid, sort of coming up over the next couple of months or so. Again, I won't run through all of those, but I will mention that those people with an interest in ITF 114, the registration system is now open, so you can register to attend, and it's in the early bird period, so it's significantly cheaper to register now than it will be in a few weeks' time. So do bear that in mind. And again, in the weekly email, I put some links to a number of events which are currently got calls for papers, including DNS OARC, UK NOF, and one other which I can't immediately remember. So you've got those coming up as well. And in fact, I should also mention that DNS OARC, the next one takes place, it's co-located with ITF 114 and takes place on the Saturday and Sunday immediately after ITF 114. So it's the same hotel, but it's on the 30th, 31st of July agenda to be finalized after the call for papers. So that's worth bearing in mind if you are thinking to register to attend in person for ITF 114, that there'll be a second event at the same hotel. So the incremental cost for doing both will be pretty modest. And then finally from me, just to remind you, this time next week, we've got a panel discussion on shared learnings from the deployment of encrypted DNS resolvers, which we're going to kick off that with a presentation on some of the learnings from Quad 9 with one of John's colleagues, their CTO, and then a number of other panel members will join the discussion. The exact sort of makeup of the panel is being finalized, but will include, amongst others, Vodafone, and Gianpaolo is joining the panel to give us an ISP perspective. It will, subject to confirmation in the next couple of days, include a couple more people, but I won't mention them until the confirmation. So expect an email from me midweek with the sort of final makeup, but there'll be a number of other providers or resolver operators also joining the panel. So it should be an interesting discussion, mainly talking about some of the sort of issues in scaling up, some of the things to be aware of. So for those organizations that are looking to deploy support for encryption but haven't done so yet, that should help ease your deployment journey. And sort of following week, we'll move to more policy-orientated call with Mallory Nodal from CDT, who's going to be talking about encryption end runs and some legal challenges from around the world. So Mallory will be giving her perspective on that whole discussion. So I think that will be certainly thought-provoking. So I think will be an interesting discussion, but as I say, more policy rather than sort of technically orientated. Right, that's probably enough from me. So let me stop sharing. I know we're almost out of time, but is there anything that anyone else wants to raise? I don't know if any of you that are involved in DNS OARC, for example, wants to sort of chime in with any indication of the likely themes or anything else, or any other points arising. And I can see on that point, Susanna suggested that maybe Paul's presentation will be an interesting one to take to DNS OARC. So hopefully one of the DNS OARC people will reach out to Paul directly to discuss that.
Yeah, I hadn't considered that, but that's a good suggestion. Thank you for saying that. And now I'll reach out further.
Fantastic.
Yeah, John Todd and I are both on the program committee. If you have questions about the submission process or anything like that, we'd like to see the abstract.
Great.
Okay, anything from anyone else, just briefly, before we run out of time? I'm seeing no hands raised at the moment, and I don't see anything in the chat. So, okay, well, on that note then, well, Paul, thank you in particular for your time and sort of running us through the presentation. I think you will get a few follow-up queries as a result, so that's very much appreciated. Thank you everybody else for joining. I hope you found that useful. Have a fantastic week, and look forward to our panel discussion on sort of scalability and deployment of encrypted DNS support same time next week. So speak to you then. Have a great week, everyone.
Yes, thank you, Andrew. First time I see the word Middlebox is not dirty. Thank you very much.
Good to oblige. Thanks very much.
Bye.
Bye all.
Thanks,
Andrew.
Paul. Thanks, Andrew.